Here we go, folks. Welcome to another super exciting delivery services learning session. Today, we're starting our journey into XCM with an overview. And this is going to take place over 3 sessions. So myself, Alejandro, and Pawan, we're going to give you an overview. And through subsequent sessions, we're going to dig deeper and deeper. But first, a little disclaimer, XCM is super complex. There's very few people that are masters at it, and we're just trying to get to that level. And the best way to learn is to teach, so I've heard. So strap in. Whether you're this guy here that wants to keep their eyes closed and just hold on for dear life, or whether you want to be this guy here and throw your hands up and enjoy it, we got a little something for you. So let's dig into it. So we have a little agenda here. We're going to start with a high-level overview, give you some terminology. We're going to talk about the 4 A's that are baked into what XCM is. And then we're to look at some transfer types, MultiLocation, MultiAsset, the XCVM, XCM, Executor, and all this fun stuff. And of course, we're going to have a code walkthrough. All right. So at a high level, what is XCM? So it literally stands for cross-consensus messaging format. And XCM aims to be a generic and extensible language for communicating ideas between different consensus systems across various transport protocols. That's a whole mouthful. So let's kind of tear it apart a little bit. Using this diagram to the right here, we can start to reason about what all that means. So XCM is essentially a language. It is a way to communicate ideas to disparate blockchains or consensus systems. So you see at the very bottom of the stack here, things that might understand XCM are parachains or solo chains. So that might be a parachain connected to Polkadot or Kusama, or it could be a solo chain, such as something built with Substrate or something that's not built with Substrate. It could be Ethereum, maybe even Bitcoin one day, who knows? Just above that in the stack, we have XCMP, VMP, bridges, relay, custom relays. This is how XCM messages are going to be transported between these layers. So XCM being a protocol, VMP being a protocol, and bridges, we're probably all familiar with bridges transporting information between disparate blockchains. So on top of that sits XCM. That's the messaging format. This is the language that is going to be spoken. And as long as these consensus systems down here understand that language, then we have a working environment where we can pass information between these environments. But how do we get these XCM messages created is going to be above them on the stack. So we have these things called the XCM Builder palette. It's actually a system of palettes, or the contract environment using built-in precompiles. So as long as you're able to write a message that, again, the XCMP or the relaying protocols can relay and the consensus system can understand, then it's going to be all great. A little bit higher than that, so later down the road, palettes or smart contracts might be able to also create XCM messages and pass them down the stack to achieve their goals in their particular consensus environments. You can also think of XCM related to cross-chain in the same way that REST is related to RESTful, if you're familiar with that. XCM, it's important to know that XCM doesn't actually send the messages. It's just the language, and we'll dig into that a little bit more right now. So XCM is the format. It is the language you're speaking, just like I'm speaking English to you now. Hopefully you're understanding me good, and we're coming to consensus on what I'm saying here. And messages are meant to have meaningful content. And so the most obvious kind of message we might want to send is a transfer message. So moving tokens from one consensus system to another consensus system. But it could also be a variety of other things, so like smart contract calls or pallet calls, or just to say hello. If one blockchain wanted to say hello to the other one, we can argue if that's a meaningful content though. XCM is not XCMP, so we have to make a clear distinction here. XCMP refers to the protocol of sending these messages. This is how XCM messages are going to reach other consensus systems. It is also used to refer to the channels that are set up between these consensus systems. Yeah, we'll dig into that a little bit later as well. So again, XCMP is just transporting the bytes that the XCM represents. All right, digging into some more of the terminology here. We kind of covered what XCM stands for already, but VMP is referring to the protocol that passes messages vertically between the relay chain and the parachains. So within that, we have two distinct types. We have an upward message passing, sending messages from a parachain up to the relay chain. And then we have downward message passing, sending a message back down from the relay chain to a parachain. And again, to cover, XCMP is the protocol, or also referred to passing. This is how messages, one way that messages can be transferred from one consensus system to another. And then within those environments, we need some way to interpret these messages. And that's where the XCVM comes in, the virtual machine that understands and interprets that language for the particular consensus system that's in. And in the interim right now, so XCMP is still the final kind of vision of this whole system. But in the interim, we have this thing called HRMP, also referred to XCMP Lite. And this is the protocol in place to facilitate parachain to parachain messaging until XCMP is fully ready. And if you've been paying attention to Kusama, or you'll have seen a lot of proposals being passed to establish HRMP channels. And these are unidirectional channels that allow a parachain to speak to another parachain. And normally you'll see two channels being set up at the same time, one going one way, the other one going the other way. And this essentially sets a bidirectional communication layer so they can send messages back and forth to each other. To cover a couple of the terminologies in terms of what is currently possible, we have these things called teleport transfers. And this specifically relates to a relay chain sending receiving messages between trusted parachains. And we're going to talk about what trusted parachains means. But as long as the relay chain can trust the destination, then we can use something called a teleport. Oops. In other cases, we're going to use a reserve back transfer. And what reserve back transfers do is it uses a trusted parachain as the reserve. In this case, we're talking about Statemint or Statemint. So there's several reserve backed assets that live on Statemint or Statemint. There's a number of assets that reserve assets, the actual assets live on Statemint and Statemint, and then you have a correlated or derived reserve backed asset that lives on another consensus system. Could be a parachain, could be anything that understands XCM. So maybe I got a little twisted there. Reserve backed transfers are what we use when we don't trust the consensus system, and so we need some way to ensure that the double spend issue doesn't occur. And so we use a reserve of actual assets on a trusted parachain to derive assets that are related to that reserve asset on other consensus systems. Sorry, speaking and terminology is hard. Okay, so now let's talk about how we identify these assets and other consensus locations. We use MultiLocation and MultiAsset, and this is a way to communicate in the language of XCM where we want to speak to, like what consensus system outside of our own do we want to reach, and what assets do we want to transfer between those. And again, a lot of this will become more clear as we dig deeper into the examples and demos. One last term here is a sovereign account. So remember, when we're sending messages between two untrusted two untrusted consensus systems. We have a intermediary, in this case, we're talking about Statemint and Statemint, that has these reserve back assets. And in order to transfer them, a consensus system is going to own an inaccessible account on Statemint or Statemint. And this is called a sovereign account. And this is what's going to be used to keep account of where tokens are in other systems, on other blockchains. Okay. Let's talk about the 4 A's. So these 4 A's are coming directly from the XCM format. Highly suggest taking a look at this if you're just starting your journey into XCM. Has a lot of great information that outlines essentially the entire XCM format. And so these 4 tenets were kind of baked in as the guiding principles to XCM. So first of all, we want asynchronous messages. So sending a message doesn't block the sender from sending anything immediately after that. And we want absolute. So XCM messages are guaranteed to deliver and be interpreted accurately in order and in a timely fashion. So this is kind of like the code is law rule, where the message is going to do what it says it's going to do. Now, mind you, there's a caveat here. This doesn't protect you from user errors. So if you construct an invalid XCM message, it will do what it's supposed to do, but it might not do what you want it to do. So keep that in mind there. XCM messages are asymmetric. So this kind of goes hand in hand with the asynchronous part. XCM messages don't have results. So when you send a message, you don't know immediately if it was successful. You're not stuck there waiting to see if it's received and interpreted correctly. It's just sent off, and then we have to do some external kind of investigations to figure out if it actually did the thing that we wanted it to do. Lastly, XCM messages are agnostic. It makes no assumptions about the nature of the consensus system between which messages are being passed. It's very much like I said earlier. I'm speaking English right now. XCM is just the language. It'll speak that language, and regardless of whether or not the consensus system understands that language. So make sure you're sending to a chain that understands XCM before you try and send an XCM message to it, essentially. Cool. Let's dig into some of the types of transfers that we currently have available to us. I mentioned in the terminology section, we have a teleport. Just as if you're familiar with Star Trek, you're literally teleporting, taking one asset on one chain. It vanishes, functionally it vanishes from that chain and appears on another chain. And a reserve back asset, a reserve back transfer, base transfer is similar, but the funds are actually going to be, the real assets are going to stay on the trusted parachain, like Statemint, and derivative assets of that real asset are going to be minted and moved, minted and burnt on the untrusted parachains, and the real assets are going to be moved on the trusted parachain. All right. Here's a diagram to hopefully to make clear all the things that I've been talking about here. So this is a diagram showing a relay chain, a teleport between a relay chain and a trusted parachain. And here's where I'll kind of unpack what trusted parachain means in this case. So if we were to send DOT to any parachain or any other chain that has a different consensus system, what the worry is that consensus system, through its own governance, could arbitrarily mint an exorbitant amount of DOT and then send it back to the relay chain and say, like, I have all the DOT now. We don't want this to happen, obviously. And so we only want to teleport to systems that we trust. And what do we mean by trust is that the governance of the relay chain, or we can have certain guarantees that the governance of that chain is not going to be malicious. And so one way we can do that is through system level parachains or common good parachains, such as Statemint or the collectives palette that was recently launched. So the governance of the relay chain has governance over those trusted parachains, and therefore we have a high level of guarantee that it's not going to be malicious. And so we can use a teleport in that case. And what happens with the teleport is you have this user, they have some number of tokens on the relay chain, and they're going to use a limited teleport, and they're going to interact with the XCM palette. I have pallets here because it's not technically one pallet. It's a collection of pallets that work together. But that's an implementation detail you guys can look into if you're interested. But essentially, the XCM pallets take in this message and say, okay, this is what's going to happen. We're going to take these relay tokens and we're going to send them to the teleport checking account. So this, in effect, is burning them because this account is not accessible in normal ways, but they do get sent to this account. Again, another implementation detail. At the same time, we're going to use the XCMP protocol to forward this message across space and time to reach the trusted parachain through the Parachain system palette. And it's going to take that in and say, okay, I'm seeing there's a message here. Let me handle this with a downwards passing it to the downwards message queue, which interacts again with the XCM pallets living on this trusted parachain. And it says, okay, I know what to do with this. And it then relays those tokens or creates those tokens and places them into the destination address. Cool. And now you can imagine if we wanted to go the other way, these lines would essentially be reversed. Instead of using DMP, it would be an upwards message passing. So use the UMP queue. It would pass those messages back across, and then the native tokens would be deposited into the destination address back on the relay chain. Cool. Now a reserved-based transfer, getting a little bit more complicated. Hopefully we can, this diagram helps illuminate that and make it a little bit simpler. So we have the user here. This time they're starting on Statemint, and they want to send tokens to a parachain. And this parachain does not need to be trusted as long as there is a channel open. Normally you want a bidirectional channel. So as long as there's a channel open between the Statemint and this parachain, then we're going to be able to send messages and token transfers to them. So the user, again, is going to trigger this, interacting with the XCM pallets. And this is going to be a number of underlying tokens. So what do we mean by underlying tokens? These are tokens that have been created, minted on Statemint, and they're going to be able to held in reserve on Statemint, and reserve-backed assets are going to be minted on the destination chain. So the XCM pallets take the amount of tokens minus fees and all that, and deposit it in the destination parachain sovereign account. This is one of those key terminologies I mentioned earlier. So this destination parachain, through the process of setting up bidirectional channel between Statemint and itself, it creates a sovereign account that is inaccessible to it, but is a place where we can keep account of how many tokens has been sent to this destination parachain. And the reason why we do this is so that if ever a number of tokens in excess of the amount in this sovereign account were to try and come back to Statemint, we'd be like, no, you're sending tokens that don't exist. So say there were 10 tokens in this destination parachain sovereign account on Statemint, and they tried to send 20 tokens back. We're going to say no, that's not legal. These tokens don't exist, and you're trying to double spend essentially. Cool. And so after those tokens have been sent to the sovereign account, or at the same time, you're going to send an upwards message to the relay chain, which is, as its name aptly suggests, it's going to relay that message. It's going to take in that upwards message pass and pass it down through the downwards message passing protocol. And similarly to the teleport, it's going to enter in through the parachain palette and pass it onto the XCMP queue, which interacts with the XCM pallets, and then those derived tokens. So now these are similar to like wrap tokens, but more concretely, they are derived from the reserve currency that exists here. And those derived tokens are going to be deposited into the destination address. And just like before, you can imagine this going in reverse. These names would be reversed instead of upwards, instead of downwards, where it says that it'll be upwards, and the reverse would happen. And now an even more complex transfer that I haven't diagrammed because it would be super hard to fit into one screen. As you can imagine, two disparate parachains trying to send tokens between each other. And so you would have another one of these here, and now we would be transferring tokens between two sovereign accounts that exist on the trusted parachain. So destination parachain A and destination parachain B would both have a sovereign account on Statemint, and the tokens would transfer first from parachain A's sovereign account to parachain B's, and then the derived tokens on parachain A would be burned, and the derived tokens on parachain B would be minted. It would be created, and that's how we keep account of where the real tokens are. They're always on Statemint or Statemint, and then where the derived tokens are in relation to those. And this prevents the double spend problem, and we also avoid the issue that you might see on EVM-based chains where you have derivative of derivatives. So if you like bridge one token to another system and then you take that and try and bridge it to another system, you end up wrapping a wrap token and wrapping that again. It gets really confusing really fast. I'm not saying this is not confusing, but it's definitely a more elegant solution to that problem. Okay. I think that's it for me. I'm going to pass it off to Alejandro to take it from here to talk about multi-locations and multi-assets.
Thank you very much. Here we will be covering multi-location and multi-asset, right? Which are like two structures of information used for defining well, all the information around referring to other consensus systems in case of multi-location, and different dashes, right? That will be like use, transfer, move, use, in those. So these two are like very like fundamental pieces of the whole like XCM format, because once you have understood like how they work and how to work with them, how to read them, to interpret like the information that they contain, right? Everything kind of like starts making a little bit more sense, right? So well, let's right into it. Starting with multi-locations. Here we have definition of relative paths, relative identifiers, that will like define of the path between two locations, right? So the interpretation of this multi-location information will depend on the contents in the context in which it will be read, right? So we can not use them like universal, like a universal identifiers of location for a certain consensus system. They are relative. All right. Examples of things that we can identify with them are, as you can see there on the slide, consensus systems, addressable accounts, data structures. So they enable us to uniquely identify one consensus system, for example, and do it like well, in this like relative manner, right? And the way that a multi-location is defined in code in SARS, you can see it right there. It's formed out of like two parameters, parents and interior. Parents, it's just number, right? It will like define the levels of consensus systems that we need to ask them before interpreting the interior information. If that sounds a little bit weird, if you're a parachain and your parameter parents is one, it's okay. Before interpreting, please go one step back and interpret like the rest of the part interior from the context of the right. Interior, we define it as junctions, right? Which will let us know what will let us define what exactly we want to identify within the consensus system we are in. Dive a little bit more into these interiors. So, well, I have the definition written in there. Always identifies a consensus system interior to the local consensus system. These multi-locations as well for multi-asset definitions are very general in the sense that they try to accommodate like all the possibilities or all the scenarios where they can be used. So that's why definitions themselves are a little bit difficult to understand as maybe the first time that you're reading them, but they fulfill perfectly the purpose, right? Okay, so when we are defining an interior, we like created from a union of all the elements that we have in that list. We can like identify a parachain, we can identify an account, we can identify a palette instance, for example, that is instantiated in a runtime of a parachain, some asset inside palette assets that is living in a certain runtime, right? If we want to exemplify this similarly to how like file systems path works, I have written there like 4 little examples on the bottom right, which will be understood in the following way, right? Like we have like, for example, the dot slash parachain 1000. What we are doing there, this will translate it to parent one dot dot go one level back. That's how it works for file systems. If this is sounding a little weird to you, then parachain 1000. So from the point of view, if we understand this, if we are interpreting this message from another parachain, will be like, okay, like I'm identifying a sibling parachain, so another parachain, which ID is 1000, right? And it's like go up to the relay chain and then like identify parachain 1000. That's like in general terms what we're writing in there. For the next example, more or less the same. We're identifying an account, but this account is present on the relay chain, right? And we are identifying it from the parachain. So please go up one step above. We're in the relay chain now. Um, like interpret like the contents of the interior. In our case, our interior is account 32 bytes, and then like the accountants, right? Following example, parachain 42 an account key. As you can see, there's like no dots slash, so we are not going up any level. This would be like a 0 for parent. So what we are identifying here is as we are not going up, we don't want to go up. That value is 0. We are on a relay chain. This identifies like a 20-byte account. The one like written in there on the parachain with ID 42. Okay. The type of the account is 20 bytes. This could be, for example, an Ethereum account that could fit in that 20 bytes. Implementation details. Okay. The last one, palette instance, 8050, general index, and one there. We are not going up anywhere. We are on the relay chain. We can go up. The parent is 0. We're identifying an instance in that runtime. And inside the instance, that palette instance, we're identifying a concrete index, which has been created within that palette. And we can do this like unambiguously, okay? And that would be like a little bit of how like these interiors will work and how we are using them, all right? So now multi-assets. This is more or less a very similar concept to multi-locations, but applied to assets, tokens. And as we are working with like not just like locations, we have to adapt a little bit like this path concept to this, right? And we do it like in 2 different ways. There's like 2 different types of multi-assets that we can use, we can define. That are the ones that are in there: abstract identifiers and concrete identifiers. each of them have their like special needs, right? Like in the case for abstract identifiers, their purpose is being able to refer to some assets existing in some consensus system in a universal way. So like that could be like identified from whenever. Like the naming will be like the same. Like imagine like as we were like seeing multi-locations that are relative, right? And you have to tailor that multi-location to refer to a certain consensus system depending on where you are, because maybe you need to go to religion or not, depends, right? From the scenario, these abstract identifiers try to generate an identification for something, for some asset that is universally like um, usable, right? Use cases for this, like bridges, and maybe like you want to refer to Bitcoin or Ethereum, right? That's like way more outside of your consensus system because it's on the other side of the bridge. But this like brings one little concern. I don't know if I should call it concern, but there is like the need of a global registry for creating like a consensus around the naming these global identifiers for specific assets, right? As we could like perfectly like give like different names for the same asset from different places. This registry will help to solve that problem. As of this presentation, I don't think there is nobody really using abstract identifiers. Obviously, this might change in the future. Sadly, I cannot like present an example for this today. But let's jump to concrete identifiers. These ones work in a very like similar manner to multi-locations. They are made of like they are formed of multi-locations. They are like relative paths to identify assets that are living in different consensus systems, right? With a concrete identifier, we can like refer to a single asset uniquely and unambiguously, and we get rid of the whole registry problem, right? Problem again. So let's see how multi-assets are defined. How do they look? And later we will create some of our own like multi-assets multi-locations. In this case, we consider the struct is formed from an ID and fungibility. The asset ID will be the one defining if we are creating an abstract multi-asset, a concrete multi-asset, right? And then the fungibility will let us define if we are working with fungible assets or non-fungible assets. Because like depending on the case, we will want to identify fungibles by an amount of tokens of this like fungible asset that we are identifying, or an asset instance within a class of some kind of non-fungible asset, right? And you can see this perfectly there, bottom right, fungible defined by an amount, non-fungible is an asset instance on the type, right? For assets IDs, on the left, concrete abstract. As I mentioned before, concrete multi-assets are basically multi-locations. They are still like relative paths. We have
Okay, maybe it's best we just move on, and maybe if he comes back, we can jump back to where he is. So Pawan, do you want to just take over?
Yeah, sure. So what we'll be discussing here or understanding here is like the XCVM, XCVM, XCM Executor, and the XCM Builder, right? So if I talk about in simple words, so XCVM is just an non-Turing complete virtual machine, like which provides us an environment like where we'll be running our XCM messages, right? And how we'll be running those messages in that environment, like in that piece, like XCM Executor comes into the picture. With the help of XCM Executor, we'll be like running our XCM messages. We'll be like executing those messages. And what XCM Builder provides us, like XCM builder just provides types and builders in order to create the configuration of the XCM executor, because XCM executor is highly dependent on the configuration, XCM configuration, which makes it actually like configurable, like so that user can user can define the behavior of the XCM, like how message will be processed and all, like using this configuration. This can be configurable. So now let's jump into the XCVM. Like it is basically a cross consensus virtual machine, like which is non-Turing complete virtual machine whose instructions are like designed to be roughly at the same level as transactions. So if you talk about as it is high level virtual machine, so what we can do here with the help of this kind of property, we can say what we can do, we can just directly predetermine the program flow, because in order to interact with the local chain state, we only have two instructions present over here, like the withdraw asset and the deposit asset, right? Withdrawing and deposit. Apart from this, there is no memory available for the other instructions. So because we don't have any other instructions over here, so like there are no explicit conditional state unconditional instructions and looping primitives, right? Because of this, because of these properties only, we can predetermine the program flow, and with the help of this, we can easily compute the execution time of an XCM message could utilize prior to the execution, right? This property makes like easy to predetermine the execution time also. If you talk about this XCVM is a register based, not stack based. Like we'll be seeing the multiple registers we have present in XCVM in the later slides. And another point here is like a message in XCM is just a program that's run on that environment, right? We are just running a program onto that environment. So that is actually our XCM message. So here we have the first register. So if we talk about the registers here, like we have several registers, like 7-8 registers present over here. So the first one, if we talk about, is the holding register, which expresses the number of assets that exist under the control of the program, but have no on-chain representation. If we take any example of like a simple example for the holding register over here, is like you can see like we have an instruction, right? XCM instruction withdraw asset, in which you can see here, like we only have one parameter, right? Multi-assets, like we are providing the location, kind of consider it as a location, right? So from where we'll be withdrawing the asset. So okay, if we are withdrawing a asset from any location, so where we'll be putting that? So here holding registers come into the picture. It is virtualization of assets, which holds the assets on the temporary basis, right? So what will happen under the hood is like when we call this instruction, when we execute this instruction, so the asset gets removed from the source and placed into this holding register. And when we perform another operation, right, consider it as a deposit asset. So deposit asset accepts contains three parameters: the assets, max assets, and the beneficiary. So beneficiary is the location where we'll be putting that, right, that asset. Assets are specifies the specific asset which needs to be which should be removed from the holding register, which we placed at the time of withdrawal. And the max assets talks about the number of unique assets which we need to pick from the holding register. So this stuff we'll be seeing on the code walkthrough part also, like how the flow executes and how this will happen, how we are putting the assets on the holding register and where holding register comes into the picture in the entire life cycle, I would say, right? The next one we have is the origin register. It basically, it just holds the location of the consensus system from where from where the current XCM execution originated. So this holding registers just for example, we have a list of instructions present in the program in the XCM message, and if you are going over chain and chain, right? So this holding origin register holds the location of a particular consensus system where that particular instruction or XCM message, XCM execution originated. So that's why we have the holding origin register over here. The next set of two registers, like why I put this both the register into a single slide, is because they both are related to the weight. As the first one is the surplus weight register. It is just expresses the amount of weight by which an estimation of an original program must have been an overestimation. You can consider, as name suggested, it is surplus weight register. Whatever the weight will be remaining at the end, like we'll be putting it into the surplus weight register. And later on, with the help of this refunded weight register, we can just we can just keep track of the portion of the surplus weight which we refunded. So that's why we have the refunded weight register also here, which just keeps track of that, so that we should don't refund the surplus weight more than one. That's why we have this register. Now, another part of the registers I would say here is like related more of the program like control flow and the exceptional handling piece, right? The first one we have here is the program register, which expresses like currently executing program of instructions, right, of the for the XCM. So whatever the program we are running in the XCVM, so this program register holds that, right, the current program of the instructions. Like we will be having multiple instructions, right, for example, in the program. And if you talk about the program counter, so as in the program register, we have multiple instructions, right, in one program. So program counter keeps track of the index. I can see a typo here, so I'll be correct that. Right. So this program register keeps track of that a particular index, or like whatever the instruction is executing, and it gets reset to 0 when program register changes. For example, we'll be having another program, I would say, right, another set of instructions. Then again, the program counter resets to 0 and incremented by one, like after every successful instruction, right, every successful execution of an instruction. The next set we have related to the errors. So error register is like expresses the information of last known error. It just keeps track of the error, and it's get populated when system encounters any error only. Else it will not be populated. And the next one again we have, if for example if system encounters any error, then how we should handle that. For that we have the error handler register, which contains any code which will be executing, like which will be triggering at the time of error. So when any error encounters into the system, right? So the content of this error register is will put into the program register. So that program register execute that piece of code, like that handling code, and in that case the program counter is also reset to 0 because now we have another program, right? Appendix register is again any code which should run at the end of the program, whether it is a successful execution or the failure one. So at the end, for example, if program counter is like complete its execution, we don't have any other instructions, then the content of the appendix register will put into the program register. And if the error handler is also empty in the case of error, then again after execution of that error handler's code, the appendix register content will also placed into the program register. Similarly, like accordingly, program counter behaves here. And another point over here is like we just talked about a surplus weight register, right? How it will get populated in the terms of in the execution. Consider we have a successful scenario where we don't encounter, like the program doesn't encounter any error and all. So what will happen? So the weights related to the error handler, right, or the error weights related to these registers will be added to the surplus weight because we haven't used that weight, right? So these are like remaining weights. So we can add those into the surplus weight. Similarly, for example, if program encounters any error. So for example, we have a set of 5 instructions present in our program, and we got error into the second instruction. So the remaining 3 instructions, right, will not execute those instructions because we got an error. So the weight of those instructions will also, put into the surplus weight register, and at the end, like we'll be refunding that those surplus weight. So that's will not charge more than required, right? So these are the set of registers we have in the XCVM, the virtual machine we have. Now we have an environment, right? Now how which helps us, which provides us a platform where we'll be running our XCM programs, right, or messages. Now, how to run those programs? So here, XCM Executor come into the picture. So this help us to actually execute the program in the virtual machine we have. So if you talk about the normal definition of the executor, is like it interprets the message and executes the operations based on the message. What are the instructions present we have into the XCM message? So it executes those instructions one by one. Why it is like another point here is like it is modular and configurable. Like why it is configurable is like XCM, like anyone can create their own XCM executor, right? But here Polkadot provides us a template which is very configurable into a manner like if you want to, you can the behavior of XCM can vary chain to chain. You can configure it as per your requirement. You can define its behavior with the help of configuration, which we'll be seeing in the later slides. So how XCM configuration helps us to define the behavior of the XCM executor or the XCM overall XCM. And later we'll be also seeing like how builder helps provides the helpers in order to create the configuration for XCM executor. So ultimately the XCM executor and its configuration decides how XCM message will interact it to the runtime. So as per the you can see here the diagram over here, like these are the instructions which will be going into the XCM executor, which is configured based on the configuration, and they both will decide how to interact with the runtime. This is how flow goes. If we talk about like this is the XCM executor, by the way, like if you look into the code, like it actually maintains or keeps track of the several states, which we already talked about in the registers, like XCVM's registers, right? The holding is same, the origin is same. Another different thing we can see here is the original origin. So this is that thing, like this is that component which keeps track of the original location from the message come from, right? From where the message come from. So it keeps track of that original register, right? The I would say the source location of the XCM message from where we executed or triggers that message. The another point we have is the trader. So trader is okay. So this is the kind of a way to buy weights in order to execute the XCM messages, and this is config state, right? We have this config present over here. XCM executor is basically generic over this config. This is the XCM config which we talked about and which we'll see in the later slides. So with the help of this, we can define the behavior. You can see here we have the error handler, which is a runtime call of XCM config. Similarly, appendix, like what are the codes we'll be doing in the program flow. The total surplus and the refunded. Okay, so the error is we already talked about in the register piece, right? It keeps track of the last known error, like whatever system encounters any error, so it will keep track of that. The total surplus and the refunded are keep track of the weights, like if we have any remaining weight, so we'll be refunding that weight and keeping track of how much weight we have. Error handler is again the like a piece of code which should be executing at the time of error. The weight is like accordingly the weight of the error handler, appendix, and the appendix weight, right? At the end, like we have the config, which is just a phantom data. So this is what exactly XCM executor looks like. This is a struct generic over the config. Now let's talk about what XCM configuration is actually. So we have several, you can see a configuration components present over here. But as we have a lot to cover, so we'll not go with every component. So we'll pick the major ones. For example, why we have the XCM sender here. So XCM sender just routes an XCM message into the right message queue, right? So if you talk about the executor, this executor is generic over this configuration. So XCM executor doesn't send message by its own. So it internally uses the XCMP, which Jorin already talked about. We have a transportation channel, right, which actually sends message from one location to the another location. So XCM executor internally uses that piece, right? And Polkadot provides UMP, DMP palettes in order to handle sending messages. You can see, like we already talked about UMP, DMP, right, in the Jorin section, but later in the coming learning sessions, you'll be seeing those into the depth. So another we have, I would say, is the is reserve and is teleport. Like let's talk about these. Like these are the filters for assets. For example, remember we have seen like the reserve based transfer and the teleport transfer, right? So with the help of these two components, what we can provide the trusted reserve and the trusted teleporter. So at the time of these operations, we can ensure that, like we'll be seeing in the code also, we'll be ensuring whether this is the trusted reserve or not, or trusted teleporter or not. If not, then we'll throw an error, else we'll continue with the program flow. The next one is let's talk about the barrier. So it defines the conditions needed to execute the XCM call. So basically, through the help of barrier, what you can do, you can define the you can decide which XCM message we should execute or not. It just verifies that whether this should be executed or not. If not, then it will not execute that. It will throw an error. Else, it will execute the message. With the help of this barrier, we can do that. We'll be seeing this the implementation of this in the code walkthrough section also. And apart from this, like we don't have anything like we have these others configuration item also. But let's talk about the asset trap, like because we already talked about the holding register. So this asset trap is just a handler for the assets when when assets are left into the holding register at the end of the execution, which we withdraw at the time of like withdraw assets, right? So how to handle those assets if they are left into the holding register. So now these are the configurations item. Like I would say, like now we can jump into the code. We can understand whatever we discussed over here. And I'm not explaining all the configuration item because like in the coming sessions we'll be having like more detail, more granular information on these XCM configuration, right? Let me quickly show some code so that we can understand how things are going internally, right? That will be more helpful. Please let me know when you guys see my IntelliJ. This is the actual point from where our execution begins, right? So this execute function, you can get this function inside the XCM inside the executor, into the lib.rs, right? Here. So this is what we have, the execute function. You can see here this accepts XCM. I'll cover it quickly. So how it will doing is like it will iterate over each instructions. You can see here this operation over here. We are picking the XCM program. We are iterating over each instruction. You can see here we have the instructions. We have like around 28 instructions present in the XCM, right? So whatever the instructions we have in the XCM message, we're iterating over each one, and one by one we are processing the instruction. This process instruction is the major point. Like you can consider it as a core of the executor, which like just doing the pattern matching over all the instructions we have, like around 28 or 27 plus, right? So let's understand, like we talked about withdraw asset and the deposit asset, right, where holding register come into the picture. So what we'll do so for example, we have withdraw asset present in our program, right? This instruction, what we are doing, we are just picking the asset. We are just picking the asset. We're drawing the asset from the location which we have provided, and from the origin, right? And we are putting it to the holding register. So this is the state where we are, which is actually virtualization of assets, right? Which keeps assets for the temporary basis. This is just the operation of the withdraw asset, right? Now, if we talk about the deposit asset, so deposit asset, in the deposit asset, what we are doing is like we are picking the asset from the holding register and putting it to the beneficiaries account, like whatever we have provided. You can see here we are picking it from the holding register by providing assets, which specifies which specific asset we need to pick, and the max assets, like what is the count of asset, unique asset which we need to pick from the holding register, and just depositing it into the beneficiaries account. So this is how our control goes from the withdraw asset to the holding register, holding to the deposit to the beneficiary account. And we also talked about, remember we talked about some is reserve and is teleport component in the configuration also. So like which we are ensuring whether it is a trusted teleporter or not. So you can see that operation, like that ensure check inside the receive teleported asset, where we are just ensuring whether this is a trusted teleporter or not, whatever we are providing. Okay, so how we provide that that configuration, like it in a pair. So right, asset and the multi-location. So this is how you can provide the your trusted teleporters or trusted reserves, right, in a pair. So with the help of those, whatever we have assets and the origin, like we are getting this from the self only, and we are checking whether it is a trusted, then we'll go with the flow, we'll do this, else we'll return the error. Similarly for the reserve also, right? So these are the operations. So this is the major part of the XCM executor. Now how builder helps us, right? If you talk about the XCM executor, this is generic over this config. If you go to this config, so here we have a lot of components present, right? We talked about XCM sender, we talked about is reserve, is teleport, barrier. So now let's see the implementation of this barrier. So it has the state should execute, which has like we can see here inside the state we have the should execute function. If you see the implementation of it, you can see XCM builder provides a lot of implementation for this. For each scenario we have like allow subscription from right? Allow known query responses. So this is how XCM builder provides helpers and types in order to create the XCM configuration. And with the help of that configuration, our XCM executor's behavior is defined. So this is how it looks like into the code. I guess we are running out of the time. Like this is what I just want to show you guys into the code, and what we have discussed, we already covered into the XCM executor part. So now, do we want to go over to the Alejandro's part, or are we good? So let me.
But yeah, let's jump over to
Yes,
Alejandro's
and-
demo quickly.
The example I was about to show after multi-location, multi-asset definition, basically it was, let me zoom in a little bit here, interface with this palette here, Polkadot XCM, this is palette XCM, from Statemint, Workmind in this case, which exposes a bunch of calls that will help us to create XCM messages, right? Like the result of this extrinsic will be like composed in a message. Here, what we're doing basically is defining multi-location, multi-assets, right? This method is asking for a destination, a beneficiary, and some assets, along with some other things that are not multi-assets or multi-locations, right? So let's have a look on how I have defined those for this case, right? So destination, we are in one parachain, we're in Statemint, Workmind, right? And I want to identify another parachain, in this case, Parity 2000, from this one. So first thing that I need to do is specify the version of the format that I'm writing, that I'm using to build this information, right? Because format can evolve, and we need to explicitly show which language we are writing, like within the format, which version of it. We are in a parachain for identifying parachain 2000. We need like parent value to be 1, go above 1 level, use one interior of type X1, one junction, because I only need to identify one element. This location is only built up one element of this parachain, and the parameter for the junction, which is like the parachain. This will uniquely and unambiguously identify this parachain from this other one. As we saw before, relative path. This could be like the result of interpreting this could be like different if the setup is not the same. The beneficiary, we are going to follow more or less the same path, but in this case, we are going to define the beneficiary from the point of view of the destination. So instead of having a value 1 for parents, we will have 0, because now we are talking on the context of the destination, and we want to identify one element, in this case an account. This is our junction. This junction takes like 2 parameters, which is network type and account itself. Lastly, multi-assets, right? As we saw, multi-assets are built out of 2 things, the ID and the fungibility. For this case, the ID is concrete, and as we saw, to keep on like adding information, basically we have a multi-location from here on, right? All this part. We are going to identify an asset that has been minted within this chain. So our context is our chain, the one that we are defining this multi-location on. So value for parents is 0, and as we are not going to use a native asset, we need to identify 2 things. So it's a union of 2 junctions, right? These junctions will be like palette instance, which index is 50. For this runtime, this is the palette assets. And a general index, which is like the index of one asset that has been minted within this palette. For this example, we are using asset 1, but imagine I would like to refer to USDT and USDT in this it has been minted with index 300. I will use 300 here. Fungibility, fungible asset, and the amount corresponding the quantity, the amount of tokens that we want to refer to, right? So this is how we can like define some multi-locations manually, but obviously, like we are working on a runtime level, things vary a little bit, and this will be like how we define an XCM message itself within the runtime. Here we don't have extrinsics, right? But what you can see there is that the XCM message is made out of XCM instructions that Pawan has already covered, that they are taken care of by the XCVM. And then like, well, each of those instructions are taking different parameters. Even so, like this transfer receive assets instruction is taking another XCM instruction within it. So what we are doing here is like identifying assets, identifying destination, and then calling like deposit assets for this like transfer to happen. Identifying the assets. Well, in this case, I have all into there. That will be like a multi-asset declaration, and identifying the beneficiary will be like the account receiving tokens. This was what what you have not seen, and I hope it was helpful. I'm sorry for disconnecting. I didn't notice.
And again, to reiterate, we're going to do this again 2 more weeks in a row, going deeper and deeper into XCM. Yeah, so looking forward to all of that. I learned so much doing this presentation, and there's still more to go.